Okay, welcome back, everybody. Let me just quickly take in-class attendance to begin with. Okay. I don't need your piece of paper. I know everybody don't worry about it. Yeah, good. All right. So let's just continue example C21, example 5.5. So this one is a sailplane. Okay. So sailplane drag polar is given. CD is equal to, like I said, this is the drag polar has two components, right? Make sure. So this is CD0 parasite plus K times CL squared. So this is the drag polar. So whatever your final design configuration come up with in software X, Y, or 5, that software will give you this drag polar. This is the drag polar for your entire airplane. This is the information absolutely essential to begin with any performance calculation. So I think one of those final purpose of using the software to design airplane is this equation. You need to squeeze out this equation by designing airplane using software. Okay, so this is essential information. Drag polar. Okay, now drag polar comes with lots of different configurations. Okay, a clean drag polar, takeoff and landing, gear down, and then flap up, flap down, gear up, both down. Okay, different configuration comes with drag polar. That's one of the software's purpose to compute those drag polar to begin with. Okay, so let's assume that we have a drag polar of a sailplane, which is given here. It has a mass of 500 kilograms, and wing area is given 20 meter square. What is its maximum glide ratio and minimum sink rate at sea level? At what airspeed are these achieved? Let's take a look at it. Move on to page 5, okay? So I'm going to continue on the sailplane analysis, okay? Okay, sailplane drag polar is given. CD is equal to CD0 parasite plus induced drag KCL square, which is given as an equation 0.01 plus 0.02 CL squared. So this is given here. So number one, maximum glide ratio. Maximum glide ratio. What's the condition? Anybody please remember this? What makes the sailplane maximum glide ratio? What's the condition for that? L over D max, that's right. Lift to drag ratio maximum. Lift to drag ratio maximum is essentially equal to glide ratio maximum. Range divided by altitude maximum, okay? So this is something called optimum glide ratio or max glide ratio. So this is the maximum range you can achieve with a minimum loss of altitude, okay? So let's find out L over D ratio maximum. What is the condition for that? What is the condition for L over D max? CDO equal to KCL squared, that's right. So in other words, this is the condition. In order to have a maximum lift to drag ratio, you need to have parasite drag coefficient is equal to induced drag coefficient. This is the condition. That's right. So from here, you can get the equation of L over D. L over D max as an equation. This is going to be equal to, essentially, this is equal to R over H max. Because of the fact that CDO is equal to KCL squared, you can say this is equal to 1 over 2 times square root K times CDO. Okay, so let's just plug into this equation. 2 times square root 0.01 times 0.02. So this is going to be given by 35.4. This is a maximum or optimum glide ratio. Okay. So what kind of airspeed this is going to happen? The speed this actually happens. The speed for L over D max. How can we get the speed for L over D max? First of all, let's find out corresponding CL for that. So CL for this condition, CDO equal to KCL is CDO divided by K. It's coming from this equation, right? This equation straight out, this is the CL for that condition. So if you plug that in, you can determine CL for L over D max. This is 0.01 divided by 0.02. Okay. So you get CL 0.707. So this is the CL for the maximum lift to drag ratio condition. Okay. Let's assume lift equal to weight, even though this is not slough, but we can assume this way because this is the power of glide. Glide path angle is very small. As a matter of fact, we want to make it as close to 0 as possible. So let's just assume lift equal to approximately equal to weight. Not necessarily true, but approximately. Close to slough, right? Because it's power of glide. Close to straight level unaccelerated flight. Okay? Which is equal to CL times Q, dynamic pressure, times wing area S. Okay? So from here, you can determine dynamic pressure Q. Q is equal to weight divided by CL S. Let's just plug in weight. Weight is mass times gravity. So 500 kilogram of mass is given. Gravity is 9.8 meter per second square. CL, we just found 0.707. Wing area is given 20 meters square. So if you compute the Q, dynamic pressure for this condition is 346.5 Newton per meter square. This is dynamic pressure, and this is a standard sea level. So let's assume standard sea level density. Density sea level is 1.225 kilogram per cubic meters. Therefore, we can determine the airspeed for this maximum glide ratio. This is square root 2 times Q over rho sea level. So let's just plug in 2 times dynamic pressure, 346.5 Newton per meter square, divided by standard sea level 1.225 kilogram per cubic meters. If you compute this, the velocity is 23.8 meter per second. So this is a speed for maximum glide ratio. Okay? And I'm going to draw a line here. So the other question here for this problem is, okay, so what is the minimum sink rate and also corresponding velocity for minimum sink rate. Let's find out, okay? So minimum sink rate, do you remember this? Minimum sink rate, what is the condition for that? Anybody? Minimum sink rate, what requirement for minimum sink rate?
The maximum endurance.
Let me think a little bit. That's right. That's maximum endurance. That's correct. But what makes that thing as an airplane's design point, as operating point wise? This is actually minimum power required point. Minimum power required. This is kind of funny because this is sailplane. There's no power. There's no engine. Why on earth you are saying that? This is something called in slough condition minimum power required. Let's just go back to note of C1. Just C1 or C2, I don't know. C2 maybe. Let me just go back and take a look at slough condition for a moment. Slough is C1, right? Yeah, okay, that's fine. Let me go back to unit C1 note, okay? Actually, master note, okay. Yeah, this is master note of unit C1. Let's take a look at the slough condition. Okay. So again, things really get confused. Don't get confused because when I was undergrad student, this is completely lost. I basically decided to go for aero, not the bright Mach. Okay, so what I'm talking about is this is the location, right? So it's different depending on propeller powered airplane, or this is a propeller powered airplane. This is the velocity for minimum power required. That actually gives you the maximum excess power. Okay. Now this is the turbojet or turbofan airplane. Minimum power is right here. This is actually different from minimum thrust. Okay. So much lower airspeed for the case of turbojet. Now turbojet, turbofan airplane, because of the engine, you cannot slow down the airplane. That's the problem. Sometimes when you keep turning on your engine, you cannot slow down. The engine's limited for lower end. That's sometimes it is an issue. And then propeller powered airplane, you can slow down much lower speed. And then usually that is going to be minimum power required point. Again, this is going to be maximum endurance like Joshua said. Okay, now this is a sailplane. There's no engine. That means if you're flying turbojet and turbofan airplane, you just cut off the engine. You can slow down to the minimum power required point. That is going to minimize the sink rate. Okay, if it's a sailplane, uprising airspeed is higher than minimum sink rate. You can still stay in the air forever. You don't need engine to stay up in there. So let's just go back here. So again, minimum power required. What is the condition? Do you remember this? This is the point that 3 times CDO is equal to K times CL squared. This is super important. I almost want you to memorize this.
Memorize?
You can memorize this, of course. Sure. Okay, so let me order you. Please memorize.
So we should not understand, just memorize, correct?
Yeah, that's right. Because that's what I'm doing. Oh, memorize. 3 times induced drag coefficient is equal to, 3 times parasite drag coefficient is equal to induced drag coefficient. This is actually minimum power required condition. Okay? We are going to look at why this is the condition. Okay? We can do that. Actually, we did it, right? Didn't we do it? I think we did it. Why this is? Why this is? Right here. right here, but I'm not explaining why. Huh? Okay. So I guess the big question is why? I need to add this next semester. Sorry about that.
You could just add it right now.
If I can, yeah, I'll do. It may take some time to research it. Okay. So as soon as I find it, I'll let you know. But definitely, I have to fix the notes for next semester. Sorry about it. Okay. Again, this is ongoing. I'm Arab guy, not the right guy. Everything is Dr. Ashworth's fault because he retired all of a sudden. Okay. So anyways, let's just take this as is right now for a moment. I really need to find out why this thing is. If I ask this, hey, Dr. Ashworth, why this thing is, and he may have the answer, he may not have the answer, I don't know. Right now, I don't have it. Do you have the answer? I don't know. I want to hear if so. There must be an explanation for this, but I need to think sometime. Okay, so memorize. That means I have no clue. That's why you have to memorize. So this is the condition for minimum power required. Okay. Now, from here, what is the CL then? CL is equal to, of course, changing the form of this equation, CL corresponding to it, 3 times CDO divided by K. Okay. So obviously CDO is given 3 times 0.01 divided by K is 0.02, right? So this is 1.225. So this is the CL required for minimum power required or minimum sink rate condition. Okay, so this is a CL. Now once again, we are going to assume lift equal to weight, which is equal to CL times Q times area S. And then from here, you can determine dynamic pressure Q is equal to W over CLS, right? Weight is 500 kilogram times 9.8 meters per second square. Why do you need to give me mass? Why don't you give me weight? But anyways. CL is 1.225. Wing area is 20 meters square. So this is going to give you 200 Newton per meter square. This is dynamic pressure for this minimum sink rate condition. Once again, this is sea level, so density is sea level. So you're going to compute B infinity corresponding to it, which is 2 times Q over rho of sea level. Okay. So once again, you're going to do the same computation. 2 times 200 Newton per meter squared divided by density sea level 1.225 kilogram per cubic meters. Okay. So this is going to be the airspeed, which is 18.1 meter per second. Hey, wait a minute. So comparing those two, the optimum condition to maximize the range, you fly this airspeed. Now, in order to optimize or minimize the sink rate, you fly much slower speed. So this actually indicates one important thing. David wants to say something. Go ahead.
Oh, I was just a little confused, I guess, because our assumption is that it's close to level flight.
Yeah, that's right.
But the lift coefficient is very much not.
Lift coefficient is different because airspeed is different.
Oh,
Wait a minute. Yeah, that's why. Yeah. Dynamic pressure is different. That's why. Yeah. Okay. All right. So the lift itself is kind of probably similar to. No, not quite. No. Lift is different too. Everything is different actually.
Yeah.
Yeah, because you're flying different airspeed. So here's the important thing. In order to maximize the range, sometimes you have to fly faster. So keep that in mind. You know, stay up in air, you want to fly as slow as possible. That's always true, usually. If you fly fairly close to star, you fly as slow as possible, you're going to stay up in air for longer time. However, if you want to fly longer range, you can't fly that slow. You need to fly faster. Okay? We're gonna discover those things one at a time. Okay? And then I know you're gonna get super confused, like myself when I was undergrad student. So I do my best to sort of summarize the entire thing at the very end. Range and endurance, those are quite confusing. Okay? So we are talking about maximum glide ratio. This is, as a matter of fact, yeah. So as a matter of fact, this is actually a range. Okay. So how do you maximize your range? Of course, lift to drag ratio maximum. Yeah, sure. And then in order to maximize lift to drag ratio, you almost always say, okay, so that means this. This is a condition that actually maximizes the lift to drag ratio. So parasite drag is equal to induced drag is going to always maximize the range, almost always. Now, this is a discussion, however, this is actually endurance. Minimum sink rate is endurance. Endurance is E. Now, stay up in air for longer time is endurance. You want to fly as slow as possible. Now, sometimes the type of engine prohibits you to fly slower than certain speed, right? So that actually making you confused. So let's be careful about that. So this is the case that range and endurance if there's no engine, sailplane, okay? Yeah, wait a minute, I forgot one thing. Let me just complete this problem, okay? So, yeah. So now, what is the minimum sink rate? Let's compute. So what is the minimum sink rate itself? Okay. So the condition for minimum sink rate quite important. Please memorize 3CDO is equal to KCL squared. This is important. And that means CD is equal to CDO plus K times CL squared. That means this is essentially 4 times CDO. That's right. Because 3CDO is equal to KCL squared. So this is 3CDO, right? Right? This is equal to 3 times CDO, right? So if you add them together, it's 4 times CDO. Do you follow? So this is the condition for minimum sink rate. Okay? So how much drag does it have? CD times Q times area. Yes, this is 0.04. In other words, CDO is 0.01 times 4 is 0.04. That's CD. Times dynamic pressure 200 Newton per meter square. Area is 20 meters square. Drag is 160 Newton. This is the drag. Maximum sink rate is, let's just go back to the equation. Minimum sink rate. Minimum sink rate equation is minimum sink. Yeah, that's vertical. It's like a crash.
It's a crash.
That's a crash, yes. But vertical go down to ground. So minimum sink rate equation, okay, requires drag by. Drag is drag multiplied by velocity is power required, of course. Drag times velocity is a power. So this is the equation. We are going to pick it up. Equation 531, we are going to pick it up and then complete this. So minimum sink rate is Okay, minimum sink rate is, if you pick up the equation, it's going to be V infinity times drag divided by weight of the airplane, which is V infinity we found 18.1 meter per second. Drag we found 160 Newton. Weight is 500 kilogram multiplied by 9.8 meter per second square. Give me a weight, not the mass, but anyways. 0.59 meter per second. So this is the minimum sink rate for this airplane. All right.
And that's just a vertical velocity down?
That's right. So this is the velocity component in vertical going down direction. So you're going to lose this much, you're going to go down this much direction, this much speed. So if you have updraft wind airspeed is higher than this, your airplane keep up in air.
Okay, yeah, so that's just, okay, that's
Yeah.
just the ratio times the.
That's right. Okay, very good point. Any question here? So we are going to continue the discussion of endurance and range. So this is the first encounter for you for range and endurance. Now later on, we are going to compute the range and endurance for two different types of airplane. One is a propeller-powered airplane. The other one is a turbojet, turbofan type of airplane. Depending on the power plant you have a different equations of range and endurance. It is going to make you confused. In other words, two more type of airplane. This is the third type of airplane. The airplane doesn't have engine, have a range and endurance equation just like this. You come up with a propeller airplane, come up with a range and endurance equation. You have a turbojet airplane, range and endurance equation. Now, range and endurance equation come up with two different types. One is a approximation method. The other one is Brigade equation, which is more like a complete type of equation. So you have a variation of total 10 equations for range and endurance for different type of airplane. Okay, so don't lose your focus. At that moment, when I was undergrad student, I gave up completely for this class, but you can't, sorry. Okay, if you want to give up, I welcome you into my research lab. You become aero guy. Forget about flight mech, like Professor Chrysler is an aero guy. I mean, he's a flight mechanics performance person, like Dr. Ashworth, Professor Chrysler. I'm an aero guy. I have nothing to do, almost like airplane. I'm a flow field kind of guy. Airplane, I have no idea kind of guy. And then too bad you cannot be like that. So you have to stay with me. Okay. So let's just take a look at next page, crime and seating. Now your propulsion system gets into play. Of course, if you're talking about crime and seating, it all depends on what kind of power plant you're going to choose, okay? So now you are going to include the thrust into your equation motion. Here we go, let's take a look. So this is the equation motion for a steady rate of crime. This is the equation motion. You apply the summation of force equal to ma in the direction of flight path, parallel and perpendicular to it. Okay, so this is going to be a rate of crime, okay? Rate of crime depending on how much excess power do you have. Your power plant is going to create the power. Power is a thrust multiplied by velocity. So this is called excess power. Power available minus power required is excess power. So this is quite important. Depend on what type of engine you're going to choose. Excess power. Okay. Obviously, if you have more excess power, you have a much steeper climb angle and then faster rate of climb. Okay. Obviously. And of course, if you have a lighter airplane, yes, that's right. So this is the equation motion for climb. You are going to apply equation motion for the flight path parallel and perpendicular to it. Now, important thing is you're now including thrust. Okay. All right. So interesting thing is best climb angle. In other words, how steep you can climb your airplane. Best climb angle or maximum climb angle. and also maximum rate of climb, how fast you can climb up, okay? So this is the equation for rate of climb, and then in order to optimize the rate of climb, obviously, for minimum power required. What's that? I've seen this. What is this condition? I told you to memorize it. Yeah, 3 times CDO is K times CL squared, right? I told you to memorize it. So this is the condition for minimum power required for maximum sustained rate of climb, okay? All right. And also seeding here. The seeding is defined as you can no longer maintain the sustainable constant rate of climb. That's called seeding. There are two different definitions. One is service seeding, that altitude where 100 feet per minute rate of climb can be sustained. That's called service seeding. Your airplane still has the capability to climb up more, but the climb rate is limited to this value. Now, combat seeding is 500 feet per minute rate of climb. Absolute seeding is like a 0, isn't it? Maximum rate of climb at 0. That's called absolute seeding. Okay, so seeding has a different definitions based on the rate of climb. Anyways, let's just take a look at example here. This is interesting, just a very simple exercise. Now, when we define rate of climb and then climb angle, interestingly, we are going to refer to the data for SRAF. Standard rebel, not the standard. What's SRAF? Steady rebel unaccelerated, right? It has that. It's not climbing, okay? Suppose airplane is flying straight rebel unaccelerated flight. This is the data set, right? So you can plot thrust required, which is essentially drag, right? This is a drag, or called thrust required. This is the thrust available TA. This is the thrust required, or drag. Okay, so this is the rebel flight information. So we are going to pick up the information from rebel flight. Then you are going to estimate climb condition. That's what we're going to do. Interesting. So you are seeing two different type of plots. You've seen it. This is thrust. No, not thrust. Oh, it is. Yes. Yeah, it is. So this is a thrust plot. Okay. This is a thrust plot. This is a power plot. Okay. So it's essentially the same airplane. One is a thrust required versus thrust available plot. If you do the same thing, basically thrust multiplied by this airspeed itself is going to give you power. So if you plot the power for the same airplane, this is a power plot. One is a thrust, one is a power, okay? Same thing. So those two information are given. What are the maximum angle of climb and maximum rate of climb at sea level for the aircraft described in these figures? And the speeds at which these occur. Assume that the aircraft weight is 6,000 pounds. How would you handle this? Okay. Okay, so let me begin with best angle of climb. So best angle of climb, condition is thrust minus drag need to be maximum. Okay, and oh yeah, that's it. I guess that's it, right? Let's just go back and take a look at once again equation. So this is a rate of climb equation. What makes this optimal? Of course, airplane weight need to be lighter, sure, but we cannot control that. So one thing we can control is thrust minus drag. If this is maximum, yeah, it's going to be maximum rate of climb. Or PA minus PR is maximum. Okay. Ooh. So best angle of climb, right? This is rate of climb. Sorry about that. Best angle of climb. That's the rate of climb. I'm already confused. What's going on here? Okay. Sorry. So this is the maximum sustainable climb angle. Maximum T minus D. Minimum aircraft weight you cannot control. So it's coming from this equation, right? So coming from this equation, T minus D should be maximum. W is minimum. That's going to make this pass angle maximum, right? That's the maximum sustainable climb angle. Condition is T minus D is maximum. That's right. That's the only condition. All right. Okay. So this is the only condition. Here we go. So how can we get this? Where is the location of either one of those plots? The location of T minus D max. Where is it? Let's take a look at the thrust plot because we're talking about thrust. So this is a thrust plot. Where is it? T minus D max is, well, this is T minus D. T minus D max occurs at the minimum drag point, right? This is D min. If the drag is minimum or thrust required is minimum, that is going to be T minus D max point, right here. So this is speed for best angle of climb. Boom, boom, boom. This data point, I don't know. What's the value here? What's the value here? Textbook says 130. So good enough. Good enough. That's right. Textbook says 130 knots. So B for what? Best angle of climb. Approximately 130 knots. You need to read off from the chart. Okay, that's this thing. Okay, good. Let's finish up your computation. So this is going to give you sine gamma, which is flight path angle, T minus D over W. T minus D maximum value is given. Okay, so from here, maximum flight path angle gamma is equal to inverse sine of T minus D over W. So we are going to plug in maximum sustainable climb angle gamma is inverse sine T minus D, which is what's D here? What's the D here corresponding to this point?
399.
Yeah, well, because textbook says 400. How about this point? How about this point? Ooh, how about this point? Thrust available. 1800 maybe.
What?
Right? Right here.
Is that what the textbook says?
Yeah, that's what textbook says. Okay, so 1,800 pounds thrust available. Subtract the drag or thrust required is 400 pounds. And the weight of the airplane, you cannot touch it, 6,000 pounds, period. Unless you eject some passengers or dump some payload. This is going to be 13.5 degrees. Okay. Here we go. So this is, okay. So of course, this depends on what type of engine you choose. It is going to determine thrust available. Thrust required is how good your design is, aerodynamically speaking, using X-Flyer 5. You're going to optimize it. If you do a terrible job on X-Flyer 5, who knows, the thrust required becomes like this. Then all of a sudden, your airplane cannot climb up, cannot sustain the angle, cannot, I mean, it's horrible airplane. Obviously, that's what you call aerodynamic design. Okay, you're going to optimize this. This is the design of aero. This is essentially choice of your engine. That's it. Okay. So this is the best angle of climb or maximum climb angle, sustainable. Okay. Next is the maximum rate of climb. Maximum rate of climb, what is it? It's going to be PA minus PR. This is the excess power. Needs to be max, right? Okay. So you need to have maximum excess power. Okay, so how can we find out such a thing? Well, so this is the power plot. You have to switch over to power plot. Okay. Okay. So this is a power plot. How can you find out power available minus power required maximum? That is essentially excess power maximum. In other words, if you take the difference between power available and power required plot, you need to find out maximum gap. In order to determine maximum gap, this is what I do. I'm going to draw a line of power available, and then I'm going to slide it over, and then that parallel line touches the power required curve. Okay, so this is the parallel line shifted downwards, and that line is touching power required curve. That's where the maximum gap located. Okay, so this is the technique you have to employ. Okay, you're going to pick up like a straight edge and draw a parallel line, and those parallel lines actually touching the power required. That is going to be a maximum gap. So in this case, corresponding to it, this is the velocity for best rate of climb. What's the value here? Any guess?
219.
Something like that, because textbook says 220 knots here. Okay. So that is the corresponding to the airspeed of 220 knots. Okay. Okay. So this happens B for best rate of climb is equal to about 220 knots. Okay. And then you're going to actually read off those two values here. So this is the power required around here. This is power available around here. Okay. So if you read off this value, 0.24, if you read off this value, this is 0.68. And this is millions of foot-pound per second. Millions of foot-pound per second. So this is actually 240,000. This is 680,000 foot-pound per second. Okay, let's be careful about that. So let's just plug in those things. Okay, so best rate of climb is equal to excess power PA minus PR over weight W. So if you compute up, this is 680,000 foot-pound per second, subtract 240,000 foot-pound per second. Okay. Divided by the weight of the airplane, 6,000 pounds. So best rate of climb you get 73.3 feet per second. This is actually 4,400 feet per minute. Okay. So, well, service seating is 100 feet per minute, and combat seating is 500 feet per minute. So, yeah. So this is the best rate of climb. So this rate of climb sustainable gets lower and lower if you start having the less excess power available, right? If you go for high altitude, of course, it's going to change. So it depends on how much excess power do you have, choice of power plant, and also how good your airplane aerodynamically speaking. Okay, that's what it is. All right. Any question? So these two plots, okay, we're going to go back over and over and over again when we compute the endurance and range and climb rate and best angle of climb, and okay. So these two plots are quite important. All right, so I hope you're ready to go on to range and endurance. This is probably most challenging contents of this class, I can safely say. Okay, so prepare to be confused, but I hope you understand the differences. Now, before we step right in, I can show you a, this is the AWA SciTech 2020 paper, conference paper, written by one of our alumni. Yeah, your man. He graduated, your aero man. Jeffrey. He wrote this conference paper, and then I think he achieved the best student paper award of AWA SciTech 2020. So this is the paper. Okay. And then too bad you lost him. He was an aero person last year of SAE. So he talks about, this is the Brigade range equation in constraint analysis for power-rated airplanes. So his approach is essentially 100% mathematical approach that when you design an airplane, come up with your airplane configuration and all that, you can sort of estimate the range. Okay? As you design your airplane and configuration comes up, you can use this series of equations to estimate the range of this airplane. And that's fairly phenomenal. Okay? And it's quite useful too. In other words, if you are trying to design a long-range airplane, this kind of approach is quite important. At the stage of your configuration optimization, you're going to optimize your configuration based on the point of view that, hey, which kind of configuration optimizes the range? Because that's what we want as an airplane of our design. Okay? So here's a challenge for you. For each team, you are actually doing phase 2 using software. Using software means the following. Using software means you can test hundreds of thousands of configurations in short amount of time. It's not hand calculation. Okay, so I'm not probably convinced you saying, hey, this is a best design, and how many configurations did you compare? Oh, just one. We have a face in this design. I'm not convinced. Especially if your wing is like a half moon kind of shape, you know, kind of, I don't know. I don't know about that. So if you come up with a half moon kind of with platform, at least you need to compare against like other things, like a tapered airplane or like a elliptic shape airplane. Is it better than those? Unless you show me that, I'm not going to buy it. Because if the half moon wing is better than anything else, you know, we should see half moon wing and flying. Right? Have you ever seen that? No, right? So anyways, using software, using software means at least I want to see a variety of design choices, you know, done by each member and then compare against. And then based on the analysis, you're going to choose it. So this is a paper. I'm going to post it on the homepage. This is a massive violation of copyright, but you know, it's Jeffrey. So yeah, he may be mad. Well, give me a break, and it's anyway at all.
I mean, technically, we all have access.
Yeah.
If it's published through AI.
That's right, yeah.
That's
Uh-huh.
right, sure.
Because you're paying tuition, that's right. So I'm going to. So I'm going to post it on Cole's homepage, so you can freely download and take a look at it. This is very, very interesting paper, okay? In other words, the guy understands flight mechanics, making Professor Chrysler really proud of it. Okay, so this is very well-written paper. Anyways, let's begin from there. So this is the range, okay? Range and endurance. I don't want to go too much today because we don't have much time, but range and endurance, it's just a quick glance of it, okay? As you can see here, have you seen this? This is like a third time seeing it, right? This is a thrust plot. So this is the thrust available against the thrust required. Now, thrust required is just basically drag. Total drag composed of parasite drag and induced drag. Now, obviously, minimum drag point is the halfway point. So this is the location where, sure, you can say CDO is equal to K times CL squared. So this is the minimum drag right here. So this is the minimum drag. Okay, so what is the minimum drag point? That's for best endurance. Ooh. So if you choose to go for best endurance, you're going to simply choose the minimum drag point. Okay. Now, for best range, it's not it. It's actually faster than that. Do you know the condition for that? Well, we're going to find out. And also, this is a turboprop, and not turboprop, turbofan and then low bypass ratio turbofan engine. So this is a jet engine prop. Now, if you're talking about propeller airplane, you cannot use this. You need to switch it to the power prop. So again, it's already confusing to begin with. Let's just take a look at the range and the endurance. First of all, turbojet and turbofan. So don't lose your focus. I'm going to only talk about turbojet, turbofan. You have two different methods to compute the endurance and range each. So total 4 equations. So for the endurance, E, if your airplane comes up with a turbojet or turbofan power plant, you have an easier method, which is average value method. This is the endurance equation for average value method. In other words, when you talk about endurance, it's flying long time by consuming your fuel. That means your airplane's weight keeps changing. If your airplane's weight keeps changing, your drag also keeps changing. So you have to keep track of the change in drags and weight at the same time. Now, easy method means, hey, I'm going to just choose the average value. So the fuel consumption is linear. I'm going to choose the average value of a drag from beginning to end. So you need only 2 points there. At the beginning, at the very end, that's it. You're not going to concern anything about how you fly it in the middle, okay? So that is easy method. The other one is something called Brigade Equation. That's something Jeffrey Chen actually did some research for that. Brigade Equation is more or less like a more exact equation. You're going to come up with the integral form. So that means you can define the function of the weight and the drag change of the airplane, and then you can express that change as a nonlinear function. In other words, in order to optimize your endurance, you can come up with your unique way. In other words, you can actually consume up fuel fairly quickly at the early point, so that make your airplane much lighter. Then that actually optimize the endurance. I don't know. You can come up with all sorts of nonlinear model to come up with to maximize your endurance. So this equation is a inherently integral equation. So this integral equation comes up with a different value if you model those change of W and D as a nonlinear function. But this is the Brigade equation. Okay. So this is quite interesting. Okay. So this is the maximum endurance for turbojet and turbofan is, of course, minimum thrust required or minimum drag point. CDO is equal to KCL squared. That's, I keep saying, this is the point for the best endurance. Okay? Now, confusing point is, let's talk about range. Okay? The range is how far you want to fly. So if you want to maximize your flight distance, not the endurance, you have to fly differently. You have to fly faster. Okay? So this is the range equation. Once again, two different methods. One is easy method. This is the range equation. It's simply whatever the range endurance equation you got from average method multiplied by the velocity. That's it. Because the range is endurance times velocity. That's the range. Okay? So this is the range equation for average value method. Interesting thing is this one, inverse of CT, this is TSFC. Drag average value divided by velocity, this is the how much nautical miles you can fly per fuel pound. This is similar to miles per gallon rating for automotives. So this is your airplanes, how efficient your airplane is. Okay? So how much fuel do you need to fly like 1 nautical miles? You have to optimize this, right? Okay. So in order to optimize this, the ratio of drag average over velocity must be minimized. In order to find out this, minimize the D over B point. This is quite important. So again, I want you to memorize it. A line from the origin tangent to the drag curve is for B for best range. What I'm talking about. A line from the origin tangent to the drag curve. Please memorize. What do you mean by that? Let's take a look at the thrust plot. Okay. A line drawn from origin, straight line, which is tangent to the thrust required plot. Right here is the velocity for best range. Okay? This is much faster than the velocity for best endurance. In other words, in order to maximize your range, you need to fly faster. Okay. In order to find that, you have to draw a line, straight line, start from origin, touching this thrust required plot, which is tangent right here. So oftentimes, if you want to find out such a point, again, you need to have a straight edge, draw a straight line from origin. This is a straight line from origin, just barely touching this thrust required curve. Then you can determine velocity for best range. Okay, anyways. So that's what it is right here. Line from the origin tangent to the drag curve. That actually is the condition for the ratio drag average over velocity is minimized. Okay? Most fuel efficient, nautical miles per gallon type of things. That must be maximized because you want to maximize range. Okay? Now range also have an exact equation. This is called Brigade equation. So again, two equations for range, two equations for endurance. This is turbojet to turbofan only. Don't apply this for propeller engine airplanes. Confusing enough? But you have to stay with me. So this is Brigade equation. Once again, this is the integral type of equation. In other words, you're going to keep track of the changing weight of your airplane as you fly. Okay, so this is Brigade equation. Brigade range equation, this is something Jeffrey Chang was dealing with. Okay, so I would recommend you take a look at his paper. Okay, all right. So this is what's causing best range. Best range. Okay. Have you seen this? Have you seen this?
Similar, but not the same.
It's, oh, that's good, because I kept believing, hey, this is the same as minimum power. No, no, no. Minimum power is, do you remember that? 3 CDO is equal to KCL squared. That's minimum power. This is not.
It is now.
It is not. Man, that blew me my head up. Because it's so similar, then one can easily believe, hey, this is a minimum power. No, 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 no. No. Okay. So this is the maximum range condition, not the minimum power. Because minimum power is 3 CDO is equal to KCL squared. Because I'm too old, I thought, hey, those two are the same. No, 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 no. It's not the same. It's not the same. All right? So anyway, so this is the best range condition. Okay. The reason here is in order for best range, you have to fly faster, especially because you are turbojet airplane, jet engine. Okay. All right. So here we go. This is the huge example, and then all the solutions given. Okay. So this is okay. Do you want to go through this in class, or do you want to go through by yourself, releasing you early? Which one do you want? I can release you early now, but I will let you do it at home. This takes some time to go over it. So this is the real data. Okay. This is a flying T-38 real data. This is the T-38 trainer in standard sea level conditions. Your aircraft weighs 12,000 pounds. In other words, 12,000 pounds means you have to pick up this data. Okay. This is the 12,000 pounds data. All right. Buffet limit is your airplane stalls out right here. Buffet limit, your airplane stalls out. This mil means no afterburner, military power. Okay. So no afterburner, military power. Okay. Your aircraft weighs 12,000 pounds. You are going to answer the following 12 questions. This could easily be cut and paste exam 2. If I'm totally unmotivated to make an exam 2, I can basically cut and paste. Hey, here's the exam 2. Go ahead, and then 1 point each kind of thing. In other words, if you don't do right thing, 0. If you do it, 1. So, do you want to go over in class, or do you want to go over it by yourself? This is actually all the solutions given here. Okay.
Bring over next class.
Right now. Huh? Okay, so it's just to go over it as much as I can today. Okay. Yeah, let's go over now. All right, so this is series of questions needs to be answered here. Okay, so this is the straight level unaccelerated flight T-38 real data. So this is the thrust plot, right? So this is the thrust available. Okay, so this is the TA. TA is almost constant, but not quite. Let's be careful. So this is the thrust required or drag. Okay. Now obviously for different airplane weight, thrust required is different. So we are going to follow through this 12,000 pounds curve. Okay. So number 1, at what Mach number should you fly for maximum endurance at this altitude? Maximum endurance. Maximum endurance. Minimum drag. That's right. So minimum drag is right here. Right here. So this is the Mach number for maximum endurance right here. Emax right here. What's the value? 0.41. 0.41. Is that right? Mach number 0.41. Maximum endurance. Okay. And question number 2. Mach number for maximum range. Maximum range. Obviously, you are going to draw a straight line starting from the origin, barely touching this curve right here. Tangent from the origin, right here, right? This is the Mach number for maximum cruise range. What is the value? About 5, yeah? Yeah, about 0.5. Textbook says 0.495.
Oh, okay. Okay.
If you say 0.5, that's fine. How can you come up with 4.495? Anyways, question 3. Yeah, question 3. At what Mach number should you fly for maximum power of glide range? Here we go. Suppose if you cut off the engine, turn this into sailplane. Power of glide range. Where is it?
That's a really expensive sail.
Yeah, that's right. That's right. Suppose emergency situation, you lost your engine, but you want to maximize your power of glide range. Where is it? Where is it? 0.41, that's right, the same point, same spot here. Minimum drag, of course. So Mach number is 0.41. Okay? Question 4, what is your maximum glide ratio for, glide ratio, we can't. Glide ratio is, okay, so what is your maximum glide ratio? Can you compute that kind of stuff? Of course, this is going to be R over H max, right? This is L over D max. So first of all, what is the condition of L over D max? What's the Mach number for that? 0.41, that's right. So you're going to choose this point, right? Then you're going to read off drag, and then what is the lift? What is the lift? About equal to the weight, okay? Almost level flight. Go ahead.
About the answer for number 3.
Number 3.
How would you achieve Mach 0.41 in unpowered flight?
That's a good question.
Okay.
You can't probably fly that fast. Okay, so realistically, yeah, that's right. So that means realistically speaking, you have to really accelerate to 0.41, then to cut off the engine, then you maximize.
But then you slow down and then you lose it.
That's right. So if it's under the emergency situation, you can never have that. Yeah,
So you
okay.
die.
That's right.
You eject.
You eject.
You probably eject, yeah, that's right. Good point. So L over D max you can compute by reading off of this minimum value here. Drag is, what's the drag? Drag is about 1,000 pounds, right? 1,000 pounds of drag. This is drag and 1,000 pounds. So 1,000 pounds of drag and lift equal to weight 12,000. 12,000 divided by 1,000. 12. Here we go. This is 12. Okay. Question number 5. At what Mach number should you fly for minimum power of sink rate? Whoa. Where is it? Minimum power of sink rate. This is a thrust, isn't it? You can never have that kind of a. You need to have a power plot, isn't it? Oh, yeah. Okay, now I got it.
Yeah, it's on the next page.
Next page.
Yeah.
That's right. That's the next page, isn't it? So the next page, you actually have a power plot. Okay. No, so this is a C-level power plot. So from here, you are going to have maximum difference here. No, that's a crime. That's a crime. Sink rate. Oh, right here. Looks right. Okay, sorry. So this is a power plot. Okay, this is also power plot, but this is a power plot. So over this power plot, you're going to come up with a minimum power required. Okay. So right here is a Mach number for minimum power required. What's the value here?
0.34.
Whoa, exactly. That's exactly what the textbook says. 0.34.
I might have read the answer on number 5.
Yeah, that's right. Next page. You have the answer, right? Okay, so next class, let's just continue on. We just to find out up to here, right? 6. So next class, let's just continue, take a look at range and then endurance, okay? All right. Have a good day, all right? Just take a look at this example exercise by yourself. Do you have any questions, people online? Have a good day. See you on Thursday.
I see you watching stupid videos, but I don't think I'll be doing much.
They're not helpful. I watched them